What if everything you see isn't even real? Not the stars, not the atoms in your body. What if it's all just ripples in an invisible field? This is the true story of the universe, from the first spark to the final question. A barren stretch of desert is dimly lit by the brightening sky. There are still 30 minutes before sunrise, but above the clouds, the stars have already faded, and a deep blue, shadowless light suffuses the desert floor. In the last few months, the flat, featureless ground has been transformed. A 30-meter-tall steel tower bearing a terrible payload stands alone at the foot of the Escura Mountains, surrounded by little more than crisscrossing tire tracks leading 3 kilometers from a now empty adobe ranch house. Beyond, situated to the northwest and south, all at a deliberate 9-kilometer radius from the tower, are 3 part-buried shelters, each with their windows turned toward their joint focus. The scientists and soldiers now encamped within these shelters cannot see the tower at the circle's epicenter, but they will soon see, all too well, the effects of its fateful payload. Not knowing what to expect, they lie on the ground, feet pointed toward the invisibly distant tower, and listen to the countdown as it crackles over the public address system. At precisely 5:30 a.m. on the 16th of July, 1945, an earth-shaking boom marked the beginning of a new era of civilization and the birth of a new branch of physics. The so-called gadget bomb, which had been hoisted to the top of the firing tower, imploded, beginning a devastating nuclear chain reaction within its plutonium core. The nuclear bomb exploded with a force equivalent to 21,000 tons of TNT. Within a fraction of a second, the steel tower was vaporized, and the desert floor melted to a green glass. Dim dawn turned to bright day in an instant, as the blast ballooned and then mushroomed into the now iconic symbol of the nuclear age. This was the Trinity Test, the first ever full-scale detonation of a nuclear bomb, which would come to shape the course of history in the field of science. The 1930s had seen monumental advances in atomic science and radiation research, and the spectacular discovery of nuclear fission in 1938 was overshadowed by the outbreak of war just a year later. But physicists were quick to realize the devastating potential of their new discovery. Albert Einstein co-signed a letter to then-President Roosevelt with a warning: "It is conceivable that extremely powerful bombs of a new type may thus be constructed." So the US developed their own bomb before any other nation could. The test was considered a great success, and just 21 days later, the United States dropped a similar atomic bomb, the so-called Fat Man, in the city of Nagasaki, Japan. If it had not been for the deadly pressures of war, nuclear science may have followed a very different and likely slower path. The exploration of the atom, one of the tiniest particles of matter, had until then been little more than a curiosity, the domain of, at first, philosophers, and then gentlemen scholars. Small improvements in experimental methods and equipment brought small breakthroughs, until the fateful revelation that atoms and their nuclei were indeed not the end of the Russian doll, a discovery that led directly to New Mexico, and then Japan. As the glow from that first nuclear explosion faded, it left behind a new thirst to understand what our universe was actually made of, and how it came to be. That journey, the quest to discover what makes up everything, would see scientists delve ever deeper down a rabbit hole of matter and mass, of fields and particles, and even further back in time in a century-long quest to answer the immortal question: what is, at its most fundamental level, everything, and perhaps even more importantly, is any of it really real at all? It was ancient Indian philosophers of the 8th century BC who first asserted that nothing we experience is in fact real. Such an extreme reductionist philosophy is simple enough to follow. A cart can be broken down into its component parts: wheels, axles, yoke. Those components can too be broken down. A wheel becomes a hub, rim, and spokes. Each succession of smaller parts can be broken down further by hand and with specialist tools until nothing remains but a collection of minuscule specks, each indistinguishable from the next. What then are the objects of our experience? Is everything, if not piles of such specks, amassed and organized to give the appearance of something greater? These looming existential puzzles were visited again by ancient Greek philosophers some 400 years later. Considering the same problem, Democritus and Leucippus came to the same conclusion. Ultimately, everything we can see and touch can be broken down time and time again until an impasse is reached, of tiny particles that can be divided no further. Democritus gave these hypothetical particles a name, defining them by their fundamentally indivisible nature, atomos, meaning uncuttable. Today we know them as atoms. And yet it wasn't until the 19th century that science, rather than philosophy, allowed researchers to probe the nature of these mysterious, uncuttable atoms. In the early 1800s, English chemist John Dalton spent his summers in the mountains of the Lake District in northwest England. Before the advent of comprehensive maps of the region, he was an authority, measuring their altitude and distances through his own hiking experience. One can imagine his mind wandering in these hills, both measuring and musing upon the remarkable theories he was forming within his Manchester laboratory, for Dalton spent the rest of his time analyzing the nature of various chemical compounds. These compounds were as distinct as the peaks he knew so well. What was it about their basic nature that made them behave so differently? All of these chemicals, he posited, were composed of simple, indivisible building blocks that related to the elements that made them up. So, methane, as a combination of carbon and hydrogen, contained indivisible atoms of carbon and of hydrogen. Nitrous oxide was built from nitrogen atoms and oxygen atoms, and so on. Unknowingly invoking the ancient philosophies, synthesizing the works of his contemporaries, and drawing on his belief in the ultimate simplicity of nature, Dalton introduced the scientific concept of the atom to the world. But, of course, as we know now, this naming process was premature. Atoms were not indivisible, not the rightful scientific heir to the ancient Greek atomos. As scientists would discover during the second half of the 19th century, while investigating the conduction of electric charge, scholars began to hone in on a different kind of particle, which seemed unique in its ability to carry electricity. It could move through a vacuum after all other free atoms had been removed, and seemed to be present regardless of the surrounding materials. By 1897, English physicist J.J. Thomson had isolated the negatively charged particle responsible for electric current, which he fittingly called the electron. Faced with this new discovery, researchers scrambled to reconcile Thomson's electrons with the 2,000-year-old theory of fundamental atoms. Electrons could travel alone, but they also seemed to be born of atomic matter. So how could the two be related? Further experiments by the New Zealand-born physicist Ernest Rutherford helped solve the mystery. By firing radioactive particles at a thin sheet of gold foil, Rutherford showed that they were sometimes reflected, sometimes deflected, and sometimes mysteriously passed straight. This couldn't happen if atoms were solid spheres that were tightly bunched together. So Rutherford suggested, and later refined, a new model consisting of a condensed, positively charged nucleus surrounded by orbiting electrons, much as planets orbit the sun. The mass of an atom was concentrated in its nucleus, in positively charged particles that Rutherford identified as protons. And as it later transpired, as with our solar system, atoms are mostly empty space. A hydrogen atom, for example, is almost 100% nothing. With the distinction between protons and electrons, the concept of the unsplittable atom had been comprehensively split. And it was split even further in the 1930s by the discovery of yet another particle that resides inside an atom's nucleus. Thus, though impossible to know at the time, this was the beginning of a steady march toward the atomic bomb. James Chadwick had spent his early academic years working with Ernest Rutherford in Manchester. When World War I broke out, he was trapped behind enemy lines and spent much of the conflict in a prison camp, where he nevertheless managed to set up a small lab and a science club with his fellow prisoners. He returned to England to finish his PhD in 1921 and pursued the thorny problem of helium's extra mass. It was well known that atoms of helium had an atomic number of 2, meaning it had 2 protons and 2 corresponding electrons. But helium's mass was actually twice what you'd expect from the mass of those 2 protons. There must be something else, heavy but uncharged, lurking in the nucleus to contribute to that mass. Through a series of inspired deductions and experiments involving radioactive beryllium and paraffin wax, Chadwick achieved what his colleagues and mentors could not. He found conclusive evidence for this mysterious neutral particle, the neutron, earning himself the 1935 Nobel Prize in the process. And so the neutron was soon seized upon as a tool for further exploration of atomic composition. Scientists began bombarding existing elements with neutrons in an attempt to increase their mass and alter the composition of their nuclei. But in 1938, Austrian physicist Lise Meitner realized that neutron impacts had the potential to do something unexpected. Instead of adding to the mass of an atom, a neutron could instead trigger that atom to split, sharing its protons and electrons between 2 distinct new atoms and releasing a huge amount of energy in the process. Meitner's colleagues Otto Hahn and Fritz Strassmann succeeded where generations of alchemists had failed, using a mere neutron to transmute uranium atoms into krypton and barium. Inspired by the biological process of cell splitting, Meitner and her colleagues named this process fission, and it would become the physical basis for some of the most destructive weapons ever created. Despite her pivotal role in the discovery and her contribution to its name, Meitner was keen to distance herself from the devastating potential of nuclear fission chain reactions. Perhaps because of this, or perhaps because of the sexism and anti-Semitism she faced throughout her career, Lise Meitner long went uncredited for her work. It was Otto Hahn alone who received the Nobel Prize for the discovery of nuclear fission in 1944. And so, in the centuries since science left philosophy behind, our understanding of the fundamental particles of matter had itself fundamentally transformed. The unimaginably tiny, apparently unsplittable atomos could in fact be split. Baryons are the particles of atomic nuclei, the protons and neutrons. Electrons are another breed of particle, known as a lepton, which inhabit a different sphere and behave in their own unique way. Understanding the interaction of these 2 types of matter helps to explain almost everything we experience and underpins all of modern chemistry and biology. But of course, this was not the end. There were still many mysteries in the cosmos that could not be explained by mere interactions of baryons and leptons. Was there more out there? Were protons, neutrons, and electrons the true fundamental particles? Or would this step turn out to be another rung on the ladder, just as it was before? The real-world explosion that began the atomic age in 1945 left scientists the tools and the motivation to dive further into the world of particle physics, to probe deeper than ever before, and find out. As a writer, James Joyce dreamed of his work surviving him, of being immortalized for centuries to come. But even he could have scarcely imagined the impact his words would have beyond the arts, in a scientific discipline that didn't even exist when he first imagined them. His final novel, Finnegan's Wake, was written in such a way as to be almost impenetrable, but nevertheless gained a cult following, and in 1964, one of those followers, we can assume, was American physicist Murray Gell-Mann. Gell-Mann was among many riding the wave of particle physics research that had swelled throughout the mid-20th century. New technologies had revealed a multitude of other exotic particles in addition to everyday protons, neutrons, and electrons. Inhabitants of this new particle zoo included other particles with mass, like pions and kaons. These weighty particles are known collectively as hadron. So Gell-Mann and colleagues worldwide now faced the same conundrum that had faced Rutherford and Thomson half a century earlier. But now, instead of searching for the fact of the distinguished fundamental atoms of different elements, scientists needed an explanation for why apparently fundamental hadrons were all similar but distinct. And Murray Gell-Mann was not alone in trying to solve the problem. While he puzzled away at the California Institute of Technology, Russian-born American physicist George Zweig also approached the issue at CERN in Switzerland. Neither knew of the other's work, and yet they both ultimately reached the same conclusion. Hadrons must not be the bottom of the rabbit hole. There must be something smaller, some subhadronic particle making them up. Zweig supposed there to be 4 component particles and called them aces, referring to aces from each suit in a pack of cards. But Gell-Mann's analysis suggested the heavy hadrons were made up of only 3 subhadronic particles. The physicist was in the habit of giving nonsensical names to hypothetical particles, and when talking about his ideas, referred to these subhadronic fragments as quarks, rhyming with pork, but he never considered how such a word might be spelt. It was only later, while perusing Joyce's Finnegan's Wake as a break from the trials of particle physics, that he happened upon the line, 3 quarks for muster mark. The new particle would be spelt Q-U-A-R-K, and it was quarks, or quarks, that sparked the public's imagination. The name stuck. Of course, all this literary wrangling was moot until the existence of the quarks could be proven unequivocally. Experience had shown that if you wanted to split an atom into its subatomic particles, then the best way was to smash atoms together and analyze the wreckage. So, it followed that to explore the fragments that made up these smaller subatomic particles, the same experimental approach would work. Only this time it would take much more energy. In 1968, the Stanford Linear Accelerator Center was just 2 years old, but was already leading the charge in high-energy particle physics. At 3.2 kilometers long, it was the longest straight-line accelerator in the world, buried 9 meters below the flat, gently rolling landscape of the southern San Francisco Bay. Here, electrons would be accelerated to mind-boggling speeds, imbued with energy up to 50 giga-electron volts, before being smashed into unwitting protons or neutrons. And from the chaotic products of this head-on collision, physicists were able to finally show what Murray Gell-Mann and George Zweig had hypothesized 4 years earlier, that these hadrons were no more indivisible than atoms had been. A proton could be shattered into much smaller point-like particles, quarks or aces, whatever they were called. They were real. The next 30 years of high-energy particle physics saw quarks probed from every possible angle. Experiments and theory combined to determine how many types of quark there were, how they differed from one another, and how they interacted to create larger particles. Now, physicists have identified 6 different types of quark, known as flavors, which are named, somewhat curiously, up, down, strange, charm, top, and bottom. Each of the 6 possesses a specific mix of characteristics, including electric charge, mass, spin, and a property known as color, which is entirely unrelated to real color. Instead, quark color helps to understand how hadrons behave in relation to the strong nuclear force that holds atoms together. By combining together in triplets, or sometimes groups of 5, different flavors and colors of quark can produce a family of particles known as baryons, which include positively charged protons and uncharged neutrons that combine to form atomic nuclei, but also the short-lived lambda, sigma, and Z particles with properties all of their own. And they can also pair up to create another breed of composite particle known as a meson. More than half a century has now passed since high-energy physics smashed open the assumption that hadrons were fundamental particles that couldn't be broken down any further. Scientists have since discovered 6 different flavors of quark and worked out all the possible ways they can be assembled to make all kinds of composite particles, however briefly. But for all the energies we can generate in particle accelerators, there is no experimental hint that there is anything more. It seems we have finally reached the bottom of the particle rabbit hole as far as particles with mass are concerned. Quarks are as unsplittable as they get. High-energy collisions have also proved that the other breed of particles, leptons, are similarly indivisible. But they, too, exist in greater variety than first suspected and include not only the well-known negatively charged electron, but also the more massive muon and tau lepton, as well as uncharged neutrino versions of each. So there are 12 elementary particles that appear to make up everything, 6 quarks and 6 leptons. Their behavior is governed by their fundamental and unalterable properties of mass, charge, spin, and so-called color. But the particle zoo is not quite complete. The 12 quarks and leptons may be the particles that lie at the heart of every physical object in the cosmos, but they alone cannot explain the processes in our dynamic universe. Why do stars ignite? What makes them shine? And why do they even have mass in the first place? February in Chicago is cold. Wind howls through the city streets, blowing inland from the shores of Lake Michigan and piling snow in heaps at street corners. A few straggling scientists, holding tightly to scarves and hats, wrestle with the door of the conference center and rush happily into the artificial warmth. The 2009 annual meeting of the American Association for the Advancement of Science is already underway, with presentations in genetics, climate science, and astronomy cramming the daily program. But this morning there is a subtle draw towards a single lecture room. Scientists gravitate from across the center, eager for an update on the hottest race in particle physics, the search for the so-called God particle, the Higgs boson, thought to be responsible for giving many particles mass. This is a true race for glory, a face-off of institutions across the Atlantic. Fermilab's glamorously named Tevatron in Illinois was competing with the brand-new Large Hadron Collider, or LHC, constructed by CERN on the border of France and Switzerland. The LHC had been built specifically for this search, at a cost of some 3 billion euros. But before the race had barely begun, CERN suffered a huge setback. Just a month after the LHC was first switched on, an explosion critically damaged several accelerating magnets in the accelerator. The collider would have to close for more than a year for repairs to take place, giving the Tevatron a clear run for victory. So now, with the LHC crippled and Tevatron leading the charge, head scientists from Fermilab took the stage in Chicago to present their progress. Addressing a packed and steaming lecture hall, they revealed that although they'd not found the God particle yet, they hoped it wouldn't be long before they could confirm a discovery. The center had been working hard to increase precision, but the problem was that nobody knew exactly what properties the Higgs boson had, or what energy of collision would produce it. The Tevatron was best placed for exploring a certain range, between 150 and 180 giga-electron volts. So if the elusive particle could be produced within these limits, then Fermilab stood an excellent chance of pipping the damaged LHC to the post. The search for the missing pieces of the standard model had actually begun decades earlier. Throughout the last half of the 20th century, colliders were constructed, smashed particles together, and helped to reveal untold variety of quarks and composite particles. And yet, even then, it was clear that this wasn't the full picture. These particles may have been the stuff of matter, but they spoke nothing of action. 4 fundamental forces govern the interactions between matter in the modern universe: gravity, which distorts space-time and sees all objects attracted to one another; electromagnetism, responsible for electric and magnetic interactions as well as the communication of radiation across vacuous distances; the strong nuclear force, which holds atomic nuclei together; and the weak nuclear force, which sometimes causes them to split apart. The ways that these forces were communicated between particles of matter came to occupy their own branch of particle physics, as a new breed of force-carrying particle was invoked, called a gauge boson. These messengers were theoretical at first: the photon for electromagnetism, gluon for the strong force, W and Z bosons for the weak force, and the graviton for gravity. As particles, they could be considered physical manifestations of fields in the same way waves on the surface of the ocean are a reflection of the movements beneath the surface. Whether they were real particles or not is a question for quantum mechanics, but one after the other, experiments did in fact detect most of these bosons, and now they sit alongside quarks and leptons in the standard model of particle physics. Only the graviton eludes us, needing such huge collision energies to produce it that we will never be able to build a particle accelerator big enough. Once they could be seen and studied, it turned out that the different force-carrying bosons had varying properties. Just like the fundamental properties of matter, they had different masses and interacted with quarks and leptons in different ways. For example, somewhat surprisingly, the W and Z bosons of the weak force seemed to have huge masses, whereas photons had no mass at all. And this question of mass was rapidly becoming a major problem for the hallowed standard model of physics. Lepton mass is minuscule, while all the quarks have more but differing amounts. A top quark has around 75,000 times the mass of an up quark. And yet, there is nothing in the mathematics of particle physics that says that these particles should have any mass at all. Despite the fact maths can predict with remarkable accuracy the earliest moments of the cosmos, there is one glaring error. Everything comes out without mass. And mass, of course, is critically important for the subsequent evolution of the cosmos. Without mass, electrons would be unable to bind protons to make hydrogen atoms. Without that hydrogen, there could be no stars, no galaxies, no light in the universe, and no... The earliest theories for the generation of mass in the universe had been proposed in 1964, around the same time that quarks and aces were first being mooted. Peter Higgs, an English theoretical physicist, along with two other Belgian scholars, Robert Brout and François Englert, arrived at a similar conclusion. They suggested that all particles came into existence near the beginning of the universe, initially with no mass. Soon after, a force field came to permeate the entire universe, and when some particles interacted with it, they somehow gained mass. This force field is known today as the Higgs field, and the only way of proving its existence was to try and find its physical manifestation, the Higgs boson. Physicists knew the Higgs would be hard to find, and Nobel Prize-winning physicist Leon Lederman referred to it as the goddamn particle for that very reason. But it wasn't long before the epithet found a more media-friendly name. The God particle was born. Of course, calling something a God particle doesn't help to dispel the mystery around an already complicated physical theory. So, in order to bring the reality of the Higgs boson into popular consciousness, the United Kingdom science minister ran a competition in 1993 for the best analogy to explain the concept. The winner, one David Miller, a physicist at University College London, described it as follows: imagine a room full of scientists chatting among themselves. A famous professor enters the room and the scientists surround them. The professor interacts strongly with their admiring fans, answering questions and signing autographs. So the professor's progress is slowed. It is as if they have acquired mass because of the field of fans that surrounds them. Each admirer could be considered a single Higgs boson. When a less famous professor enters the room, they might only attract a smaller crowd and find it easier to move through, as if they have less mass. While imagining the effects of the Higgs field and Higgs bosons may require some mental gymnastics, actually finding the elusive particle was an even greater challenge. The Higgs boson can be produced from very high-energy hadron collisions, but instantly decays into electrons or photons. But physicists didn't know exactly what energy would produce them, or what they might decay into. So, sifting through the collision debris for one thing that couldn't be explained by the other particles of the standard model was like looking for a needle in a haystack. And so, in the end, despite Fermilab's assertions in Chicago that they could have evidence for Higgs by the end of 2009, no such evidence ever materialized. And when the Large Hadron Collider fired back up and started its experiments at the end of that year, the Tevatron's hopes began to fade. The sprint at the start turned into a grueling marathon that lasted until 2012, with 1,000 billion proton-proton collisions in the 27-kilometer-long accelerator. But on the 4th of July, CERN finally announced their success, a definitive detection from two of the LHC's instruments, both with enough statistical confidence to discern it from the background noise. The Higgs boson and the Higgs field really did exist. Nearly 50 years after they first conceived their theory, Peter Higgs and François Englert earned a Nobel Prize for the final piece in the Standard Model puzzle. Now the Higgs boson sits alongside 60 other unique, fundamental, elementary particles that make up the Standard Model. The current model includes not only ordinary matter but also antimatter, with opposite charges but otherwise identical properties, which make up exotic composite particles and annihilate with normal matter on contact. There are 36 different flavors and colors of quark and antiquark, various leptons and antileptons, plus the gauge bosons and the singular Higgs. As far as we can tell, the Standard Model is complete. These 61 particles are enough to explain everything that happens, or has ever happened, in the history of the universe. And using this structure and further advancements in particle physics over the last 50 years, science is finally in a position to zoom out from the unimaginably microscopic to the unfathomably huge, and consider how the tiniest pieces came to build a universe. When physicists try to calculate the number of fundamental particles in the observable universe using known ratios, measured distances, and established masses, the number they arrive at is almost unimaginably huge. Counting only the quarks that make up the protons and neutrons in hydrogen and helium atoms, and the electrons that are associated with those atoms, the count reaches more than 3 vigintillion, that's A3 followed by 80 zeros. Yet even with this staggeringly large number of particles, when they are spread across the vast volume of the observable universe, they average out at about 1 quark-sized particle per cubic meter. It may come as no surprise that the majority of space is actually empty space, or at least, it isn't matter. For all its experimental completeness, the Standard Model falls a long way short of explaining the makeup of the universe as a whole. Because in reality, only 5% of the stuff in the universe is what we would consider normal matter, the stuff that makes up stars, planets, and human beings. The rest is shrouded in mystery. Dark matter, thought to be responsible for structuring the universe on the largest scales and holding spinning galaxies together, makes up some 25%. It is more than 5 times more abundant than the particles of the Standard Model, even though we still don't know exactly what it is. And finally, the remaining 70% of the cosmos appears to be dark energy, the mysterious force that seems to be linked to the modern universe's accelerating expansion. If we know little about dark matter, we know even less about dark energy, despite its overwhelming predominance. These vast mysteries may still elude us. But for the matter that we can touch, see, and experience, we can reconstruct a history that stretches back to the first fraction of a second after the Big Bang. 1 trillionth of a second after the beginning of the universe as we know it, the strong, weak, and electromagnetic forces were united into a singular great force. And particles, if they were present at all, would be very different to how we understand them today. There would be no gluons, photons, or W and Z bosons, only perhaps a single type of boson which would become the progenitor of all other particles to come. As the cosmic temperature drops and exponential inflation takes place, the fundamental forces in their boson messengers begin to emerge. But they are still not as we might expect. They are massless, and with temperatures and energies still too high for particle interactions, their distinctive behaviors are not yet realized. It takes a relative eon for things to change. Around 1 trillionth of a second after the Big Bang, when the nascent cosmos has cooled to a mere quadrillion degrees, the Higgs field finally emerges. Throughout the volume of space, bosons, quarks, and leptons interacting with the field acquire mass, and some of the expected particle interactions begin to take place. It is still too hot, however, and the particles still have too much energy for quarks to bind together into anything greater. And so they exist as a turbulent and well-mixed quark-gluon plasma, the ultimate cosmic soup. Now, it has all the ingredients for the universe as we know it, but it will take the next 370,000 years for it to congeal into something we might recognize. The young universe must climb step by step back out of the hole that particle physics has excavated. Quarks must assemble into composite hadrons. Protons and neutrons must come together to form atomic nuclei, and electrons must bind to those nuclei to form the first uncharged atoms. Atoms combine together into molecules and finally assemble the physical objects of the universe. Everything we've seen and experienced today is just an unimaginably complex Russian doll of ever smaller particles nestled inside particles. Except it isn't. There is one final layer of reality to peel away, for it is by no means certain that particles even exist at all. At the smallest possible scales, the kind of scales at which individual quarks, leptons, and bosons exist, quantum mechanics is law and cannot be ignored. At its heart, this theory considers the fundamental units of matter as existing simultaneously as both a particle and a wave. Thanks to quantum uncertainty, it is impossible to pinpoint both the precise position and momentum of moving particles, meaning that they are, at best, described by a probability distribution rather than a single point. It is simply not possible to capture a single electron or quark and hold it in your hand or between minute quantum tweezers, because quantum field theory says it probably isn't there. It is little more than a transient peak in the quantum electrodynamic field, which will all too quickly flit away. From this perspective, the very concept of particles that fill the cosmos is a simplified quantization of expansive, ever-varying fields that are woven through the fabric of space and time, not just the Higgs field or the electromagnetic field, but also many others, all overlaid and interacting with one another. There are thought to be 24 separate quantum fields that permeate the universe, 12 for the various fundamental forces including mass, 9 for the quarks, and 3 for the leptons. Like ripples from raindrops in a pond, the peaks and troughs of these independent fields interact and interfere with one another, creating semi-stable patterns and larger peaks whose effects propagate further than the tiny ripples that made them. These interference patterns come to define the larger composite particles, the protons, atoms, and molecules of our experience. And so, that is the bizarre truth that lurks at the bottom of the rabbit hole. With the universe composed only of interacting fields at its most fundamental level, the tangible matter that we cling to so fervently may in fact be little more than a vigintillion passing ripple of quantum energy. When Indian philosophers nearly 3,000 years ago imagined that nothing is real, they couldn't have known how right they were. You've been watching The Amazing Universe. Don't forget to like and subscribe and leave a comment to tell us what you think, and we'll see you next time.